Hey everyone, welcome back. Quadratic forms, lecture 2.
Okay, thanks for that great introduction. So,
It's either too much or too little.
yeah, all right. So after my first lecture, some students approached and brought up a point that I actually hadn't realized or considered that, of course, not everybody has necessarily seen generating functions. The terminology generating a function might not be familiar, and one question in particular was like, what are they and what's the point? So the term generating function just means some kind of an object, maybe a power series or a Dirichlet series, where you take a sequence of interest and it's placed in as the coefficients. And I never actually explained yesterday, like, why would you want to do that, right? So like, so, oops, hold on a second. Right, so why would we want to study a sequence of numbers using maybe a power series or a Dirichlet series? Let me point out the Dirichlet series for a sequence of coefficients does not have an A0 term. There's no term for n equals 0. Power series starts at n equals 0. Of course, A0 still might be 0, but in any case, right, so why would we want to do that? And so as an example, for instance, if AN were with a Fibonacci sequence, then you can use the recursion for the Fibonacci numbers to show that the power series with Fibonacci coefficients is a rational function. And if you expand that by partial fractions and expand the pieces into geometric series, you can derive the famous Binet formula for the Fibonacci numbers. So that's maybe the primary first wow application of the concept of a generating function that you might see in a discrete math or combinatorics course. But here we're interested in Dirichlet series, which are not really formal objects in the same way that power series can sometimes be treated. There's a question in the front. Oh, yes, sorry about that. Yeah, okay. Right, the constant term, if you took the Fibonacci recursion and you ran it backwards to be true at n equals 0, you'd need the f0 to be 0, so it starts with a linear term. Yeah. Okay, so on the other hand, like, yeah, why would we want to, what can we get out of a Dirichlet series? So that was a power series example. And so here, let me tell you an example of a property of a sequence that you can get from knowledge of the Dirichlet series that has it for its coefficients. So if you have a sequence of non-negative numbers and the series, the Dirichlet series with these coefficients converges to the right of 1, and you assume that this that the series is analytic in a half plane where it converges, just like a power series. If it converges at a point, it converges at all smaller numbers on a disk. If a Dirichlet series converges at a point, it converges on the half plane to the right of there. So if the series has an analytic continuation to the line 1, continuation to that boundary, except maybe at the number 1, where there might be a pole at most, at worst, a simple pole at s equals 1, with residue r, then the average value of the sequence, if you sum the terms up to x and divide by x, that tends to r. Okay. So, for example, if you took the function, for instance, say, the Riemann zeta function divided by the Riemann zeta function at 2s, this turns out to have a series representation whose coefficients are the absolute value of the Mobius function. That's that function that's plus or minus 1 if n is square free and depending on the parity of the number of prime factors and 0 otherwise. So take the absolute value, which this is the series that's 1 over n to the s in the terms when n is square free and otherwise it's 0. So this thing converges to the right of 1. And this theorem is actually applicable to this series. It's going to has a continuation to the line real part equals 1, except for a pole, simple pole at s equal 1. And you can use the theorem to, right, so this theorem would imply, there are much simpler ways of doing what I'm about to say, but just as an example, this theorem would imply, for instance, the number of square-free integers up to x grows like 6 over pi squared times x. Again, this can be proved in a much, much, much simpler way, but just as an example, if you knew the analytic behavior of this series on the line real part equals 1, you can derive things about averaging the coefficients, which amounts to counting square-free numbers. And as another example, if you can apply this to the negative log derivative of the zeta function. It's not all obvious, if you haven't seen this stuff before, why you would ever think of such a thing. But this is a Dirichlet series that only lives on the prime powers. Its non-zero terms are only where n is a prime power, and the coefficient of a prime power denominator, like 3 to the s or 25 to the s, is going to be the log of that prime number. So this has non-negative coefficients, and it converges for the real part bigger than 1. And that theorem above can be used to deduce the prime number theorem, which has many equivalent formulations, and one of them pops out if you apply that theorem to this example. So I'm just showing that if you understand the analytic behavior of certain kind of Dirichlet series, you can deduce some properties about, say, the average value of the coefficients, and that can be used to deduce other things. Like, for instance, this is one of the ways of proving the prime number theorem. Okay, so yeah. So with experience, one comes to appreciate the idea of using different kinds of generating functions to study different kinds of sequences. But at first, it's not at all obvious that this thing would have any relevance or be of any interest. But development of math has shown this is a very useful idea. Okay, so also I wanted to address a question that came up yesterday. Someone asked, how would you check that a quadratic form is positive definite? And what was the answer that I gave? Anybody remember? Well, the discriminant is not going to give you complete information, but I had mentioned a method. The discriminant alone, its sign is not going to be enough. We're not just talking about binary quadratic forms. So I see my answer did not leave an impression on anybody. Eigenvalues, right? That I said positive definiteness was equivalent to the eigenvalues, right? So yesterday I said if you had a quadratic form, I said it's positive definite if and only if the eigenvalues of A are all positive. Now, this would, of course, require, to apply this, you would actually have to calculate the eigenvalues. Now, of course, it's not hard if you're on a computer just to whip up the eigenvalues on some computer algebra system. But I do want to point out that there is a way to, all we really care about is the sign of the eigenvalues. We don't actually care about the numerical magnitude, just are they positive or negative? And so there is a way to tell, the eigenvalues being the roots of the characteristic polynomial, there is a way to tell that a polynomial has all positive roots by using a very old piece of algebra called, I don't know, does anybody remember? Maybe in high school? I saw this in high school, a technique. Yeah, Descartes' rule of signs. So you can use, first interesting use of Descartes' rule of signs. You can use Descartes' rule of signs, right, to check that the eigenvalues, which of course are the roots of the characteristic polynomial of A, are all positive. It amounts to showing, check that the coefficients have alternating signs. Plus, minus, plus, minus, plus, minus, all the way down. Right. So you don't actually have to calculate the eigenvalues. You just calculate the characteristic polynomial. You just stare at the coefficients. Right. So anyway, okay. So, so what I would like to do eventually is explain, for instance, how do we get the analytic continuation of the zeta function of a positive definite quadratic form. But before I do that, it's likely that some people have never seen an explanation of the analytic continuation of the simplest Dirichlet series. Well, I guess the simplest Dirichlet series is the zero series. But anyway, the simplest interesting example, the Riemann zeta function. And so the analytic continuation of the zeta function of a positive definite integral quadratic form is modeled on, or can be modeled on, the explanation of the analytic continuation of the Riemann zeta function. So I want to go over the analytic continuation of the Riemann zeta function as a kind of template so that when we do the case for quadratic forms, you'll just see it's very similar process. There are some steps that are a little bit more complicated, but the general approach is very similar. So we're going to do, we're going to look at the analytic continuation of the Riemann zeta function. Okay. To prepare us for the analytic continuation of the zeta function of a quadratic form. Now, should you say meromorphic continuation? I don't know, whatever. Anyway, there could be a poll. Okay, there will be a poll, but we'll say analytic continuation anyway. So as a first step, and I realized that yesterday I presented I just stated the analytic continuation of the zeta function of a positive definite integral quadratic form, and I threw in the gamma function, and maybe some people haven't seen the gamma function. So let me just remind you, because it plays a role in all of this stuff, where the gamma function comes from, what it is. Right, so it's defined as an integral. Right, so it's given by, on a half plane, x to the s dx over x. And this integral converges not just for the real part of s bigger than 1, but the real part of s bigger than 0. Okay, so to the right of the imaginary axis, this integral converges, it's analytic, and this defines the gamma function, and generations of students have been bothered by x to the s over x. Why is it x to the s minus 1? So see, I'm writing it to isolate x to the s and 1 over x separately. And dx over x is very nice as something you integrate with respect to on the positive numbers because it's unchanged under a multiplicative change of variables. If you replace x by 3x, dx over x is the same. So you can think about it being nice in that way. So in any case, we have this function to the right of 0, but we can progressively continue it to the left of the imaginary axis strip by strip. If we use integration by parts, then you can show that gamma of s plus 1 is s gamma s for the real part bigger than 0. And therefore, you can solve for gamma of s. And the great thing about this formula is that the right-hand side actually makes sense on a wider region for the real part of S bigger than -1, except you're going to wind up with a pole at S equals 0, because when S is 0, the numerator becomes gamma of 1. Gamma of 1 is the integral of e to the minus x over the positive numbers, and that's just 1. So you're going to have a simple pole at 0, and then you can take this formula for gamma of s. This defines the gamma function for the real part bigger than -1. But then if you look at the right side and you replace s with s plus 1 on the left, then you can find a new formula for the gamma function that makes sense to the right of -2. So I can use this for the right of, to the right of -2, and so on. So in this way, strip by strip, you can extend the gamma function to the entire complex plane, and the only place you have a problem is at 0 and the negative numbers, with poles, simple poles at 0 and the negative numbers. 0, -1, -2, and so on. And the residue at the poles at -k, the residue of the gamma function at the integer -k is -1 to the k over k. So this was a unique time I had to use I used a calculator in a math class in college. This is before the internet. A take-home exam question was, what's the residue of the gamma function at negative integers? Like, I don't know. And so I just whipped out my HP calculator, and I kind of numerically approximated gamma function near negative integers until I caught on to what the pattern was. And anyway, of course, now you have Wikipedia, and anyway, AI will solve the problem for you. So anyway, but it's an interesting exercise to do on your own. Anyway, okay, so the point is this gamma function is an interesting transcendental function, and it plays a role in the analytic continuation of the Riemann zeta function, or the zeta function of a quadratic form. So, so Riemann's theorem is that if you take real part bigger than 1, the function, maybe we'll call it the completed zeta function, pi to the minus s over 2. By the way, that's a capital zeta. It's not a capital Z. I know it looks like it, but pi to the minus s over 2, gamma of s over 2 zeta of s. So this function has an analytic continuation to C. Except for simple poles at 0 and 1 with respective residues, I think -1 and 0. Well, I'm sorry, -1 and 1. And so then once you have this function, you can then use it to define the zeta function by solving for it. If you take the completed zeta function, multiply by pi to the s over 2, and divide by gamma of s over 2, so then this gives an analytic continuation of the zeta function, the Riemann zeta function, to the complex plane, except what happens to the poles? So the completed zeta function, I said, has a simple pole at 0. In the denominator, gamma of s over 2, well, gamma of s has a simple pole at 0, so gamma of s over 2 will as well, and those will cancel. So the zeta function, the Riemann zeta function, doesn't have a pole at 0, but it will have a pole at s equals 1. Simple pole at s equals 1 with residue 1. Okay. So the goal here is to look at the completed zeta function and work out properties of that, and then afterwards you can solve for the Riemann zeta function and get things for that from what you know about the completed zeta function. Okay. Of course, Riemann, I mean, he was the first one to ever think about these Dirichlet series with S being a complex variable. So he did not know the theorem already. It's not at all obvious why you should be multiplying zeta of S. Oh my God, I left out something important. Has analytic continuation, and also we have the functional equation, value at 1 minus S is equal to the value at S. Yeah, right. So Riemann had first worked out an analytic continuation of functional equation for the zeta of S directly and got a pretty ugly functional equation for it. And afterwards, he noticed that if he wrote instead this function, capital zeta of S, z of S, that it has a much cleaner looking functional equation. So he gave a second proof that emphasized this function first. All right. So how are we going to do this? Are there any questions, by the way? Okay. So we're going to start off with the gamma function as an integral. So to the right of 0, we can write the gamma function as an integral. And so if I look at pi to the minus s over 2, gamma of s over 2, s over 2 has positive real part, so I can write an integral of x. How did I write it before? I wrote it with the exponential part first. So, whoops. E to the minus x. The parameter is only showing up in the exponent, s over 2. And now let's bring the power of pi on the inside. We'll write x over pi to the s over 2. And now let's do a multiplicative change of variables. Let's set y equal to x over pi. And then you can check dy over y equals dx over x. The pi is going to cancel. And so, so this pi to the minus s over 2, gamma of s over 2, has an integral representation. E to the minus x is pi y, and x over pi is y to the s over 2 dy over y. Okay, so that's a formula for this as an integral. And now what I want to do is multiply this by the zeta function, which is only defined to the right of 1 initially as a series. And so to the right of 1, if I take this number and multiply by the zeta function, I guess I should probably move this over. So this completed zeta function, if I move these terms to the inside, pi to the minus s over 2, gamma of s over 2, times 1 over n to the s, then I can treat the term pi to the minus s over 2, gamma of s over 2 as that integral, and I can move the 1 over n to the s on the inside. So let me bring n to the s on the inside of the integral. So I'm summing all these integrals, and I'd like to make the exponents match. So to make the exponents match, I guess I need to write n over n to the s as n squared. So when I raise it to the s halves, oh my goodness, yes, everything is, I left off dy over y, dy over y. Yeah. So now we have another multiplicative change of variables. Let's let u be y over n squared. For each of these integrals, n squared is a fixed number. So du over u is dy over y. And so the completed zeta function now is a series with integrals. E to the minus pi, what was y? U is y over n squared, so y is n squared u. Y over n squared is u to the s over 2, du over u. So now we have a new integral. And I have a series of integrals, and so one can justify the swapping of the sum and the integral. And so now we get an integral with a sum of e to the minus pi n squared u, and the sum is over n, and nothing else depends on n, so I can take the other part out. And so now we have this series of decaying exponentials. So in the mid-1800s, I mean, this is a famous thing. This is nearly an example of Jacobi's theta function. So, right, so inside the integral, there's a very famous series called the theta function. So let's call it theta of u, but it's given as a series over all integers of that expression, e to the minus pi n squared u. For positive u, it converges. So the thing on the inside is the sum over positive integers. Here we have a sum over all integers, but if I extract the constant term when n is 0, and the terms at n and minus n are the same term, so I can just double the sum over the positive integers. And so I can relate the full series to the series that's actually showing up. And so the thing is that the full series has a really useful transformation property that this kind of half series in the integral doesn't have. So it's convenient to write everything in terms of the theta function. So I guess if I take out the constant term and then divide by 2, then I have a description of the completed zeta function in terms of the theta function. Okay, so this is for the real part bigger than 1. Any questions? No? All right. So where is there a problem? And if you look at this series, right, it's 1 plus, the first time you have maybe I'll emphasize here. How about I'll go up here and point out that this series here, the first term is e to the minus pi u, then it's e to the minus 4 pi u, then e to the minus 9 pi u, and so on. So if u is moderately large, this thing converges very quickly. When u is any positive number, it will converge, but when u is extremely close to 0, this series is kind of a tricky thing. This integral is kind of subtle near the lower bound of integration. And so what we would like to do is break up the integral into 2 parts from 0, 1, and 1 to infinity, and then turn the interval from 0 to 1 into the interval from 1 to infinity by replacing u with 1 over u. And so to prepare for that, I'm going to now tell you a super important property that I think is due to Jacobi, that for positive numbers, theta of 1 over u is square root of u theta of u. This is not obvious, and this is a very, very analytic statement. This is not some formal algebraic identity. Okay? And so we're going to use this. And a thing I want to point out, you see in this equation, suppose I gave you u was extremely small, maybe u is 1 over a million. Notice how if I solve for theta of u, see if on the left side, if u is 1 over a million, you may think, how can I calculate theta of 1 over a million that's really close to 0? But it relates it to theta of a million, which of course is much more rapidly convergent. So this transformation formula is also very useful numerically if you wanted to calculate the theta function, especially at numbers that are very close to 0. Anyway, so the proof of this is very analytic. I'm not going to go through it right now. I want to continue to show how this is applied. So that the proof of this uses the Fourier transform and the Poisson summation formula, just to throw some words out there. And if time permits, at the end, we'll see briefly how that comes together to help us here. But we can understand the transformation formula here without knowing necessarily how it's proved. So let's actually apply this and to the case of the zeta function. So here we have the completed zeta function described in terms of the theta function. Remember, when you see the -1, you're subtracting off the constant term of the theta function. And then we have this identity. And so we're going to combine these together to give a meaning to the completed zeta function for s outside the plane to the right of 1. And so, let's use this. Okay, so what I'm going to do is I'm going to take the integral that defined it up there at the top from 0 to infinity. I'm going to break it into two parts, 0 to 1 plus 1 to infinity, okay, of this expression. Hopefully this abusive notation is understandable. U to the s over 2 du over u. Okay, and so what I'm going to do now is I'm going to turn the integral from 0 to 1. I'm going to replace u with 1 over u, so 0 goes to infinity, 1 is fixed. Now I'll bring everything, I'll write it more properly. I'll write everything in terms of 1 over u, d1 over u over 1 over u, and then I go from 1 to infinity. Okay. So what happens, what's the deal with this piece over here? This thing over here. If you differentiate 1 over u, you get -1 over u squared. Divide by 1 over u, you multiply that by u minus u over u squared, -1 over u. Okay, so of course I know that it's backwards integration, but if you actually calculate the derivative of 1 over u, you're going to wind up with du over u with an overall minus sign. In fact, actually, here, I'll just tell you, I mean, in general, whoops, right, this, if I gave you for any integer n, du to the n over u to the n is n du over u for all integers, right, even negative, okay? But here we're applying it when n is -1. So we get minus du over u. Now that minus sign behaves very nicely with respect to the backwards integration that we're seeing. And so what we're going to do is we're just going to reverse the order of integration, and it was already backwards, and so we're in good shape. So that minus sign lets us reverse the order of integration. And now,
You added a minus
I did?
to the exponent on the left.
Oh, my goodness. Thank you. Okay. Okay, and so now, remember, the theta of 1 over u has a formula for it, right? Where's that transformation formula? Theta of 1 over u, in green up there at the top, it's root u theta u, yeah? So now we're going to change this to root u theta u minus 1 over 2. And that minus sign, I've removed it because I swapped the order of integration. Okay, great. So now we have two integrals. And one issue we have here on the left is that, remember, the theta function has that constant term. And so I'd like to get rid of it. So when I have root u times theta of u, I'm going to take that theta of u and subtract 1 to get rid of the constant term, but of course I have to add 1 back. Okay. All right. So, and by the way, this principle of what's happening here is we're trying to avoid integration near 0. And so the reason why we split the integral at 1, at the number 1, is because we're going to turn the interval from 0 to 1 into 1 to infinity by sending u to 1 over u, and the fixed point for that is, of course, at u equals 1, so that's the splitting point. If I was going to do a change of variables sending u to 2 over u, then it might be nice to split the integration at the square root of 2, because that's where 2 over u is equal to u. But here, we flipped u to 1 over u, and those are equal at 1, so that's where we're going to split the integral at 1. So now both integrals are running from 1 to infinity. And so I'm going to keep theta of u minus 1 together. We have that. And then we have what's left? Square root of u times u to the minus s over 2. And then we have the last integral. I'm counting on Jeremy to make sure that I didn't lose any terms. Does it look okay to you? So far. Yeah. I think that's, no. Do you see the mistake I made? Yeah, that minus, so here's, let's be very careful here. This is minus 1, plus 1. Right, this plus 1 is connected to a square root of u. And so I should have written this as square root u minus 1. Does it look okay now? Assuming your eyes have not glazed over, which is always a danger. Right? I mean, the thing is, we use the transformation formula, and then we took away the constant term by subtracting and adding 1, and we kept the theta of u minus 1 together, and then everything else, there's a term, square root of u minus 1. Yeah, that whole thing. Okay, great. So now, if you look, now here's the amazing thing, and I should have emphasized this point, that if you give me any positive number, and you integrate, that's a c, that's not a 0. If you integrate down to a positive number, and you took any power of u, this actually converges on the entire complex plane. Okay, this is an entire function. As long as you're integrating down to a positive number, theta of u minus 1 is a sum of these decaying exponentials, and that decays fast enough that no matter what exponent you insert on u, you can take a positive number to any complex power, that integral actually converges and it's analytic in z. And notice that the two integrals we see here, oh, what did I just do? This integral and this integral look nearly the same. The only difference is in the first one, the square root of u can be combined with u to the minus s halves. You have a u to the 1 over 2 and a u to the minus s over 2. You could combine that to a u to the 1 minus s over 2. And that looks just like the second shaded integral there on the right side, where we now just have u to the s over 2. And so we do have to deal with that middle integral. How do we know that even makes sense? But we'll come back to that in a moment. So now we can, if we combine the two shaded integrals, we'll do the theta, take away the constant term over 2 first. And in the third integral, we have a u to the s over 2. In the first integral, the square root times the u to the minus s halves is u to the 1 minus s halves. Right? That's the square root of u times u to the minus s halves. And then we have that leftover thing. What in the world was that? That's u to the, oh God, 1 minus s over 2 minus u to the minus s over 2. Anyway, so we have something here. Now, up to this point, the real part of s is bigger than 1. So, so what's the story here? So you can check for yourself that for the real part of z bigger than 1, that if you're going to integrate from 1 to infinity of du over u to the z, that's always going to be 1 over z minus 1. So that's just a calculation that you can do. And so what we're going to deal with now is just look at this thing and look at this thing. And so this integral u to the 1 minus s halves minus u to the minus s halves Everything's divided by 2u du. So if I integrate the first thing, if I bring it downstairs as u in the denominator, u to the s minus 1 halves, plus 1 is u to the, I think that's s plus 1 over 2. Can somebody check? Is that right? Bring down the u to the s halves and a square root of u upstairs and u downstairs. Yeah, that's correct. And then I'm going to subtract du over 2u to the 1 plus s halves. Yeah? And so we're going to think about each of these. You know what? I'm going to, let's give it a different color. What color do you want? Okay, we're going to use yellow. You're too late. Deadline passed. All right. So these two blobs in the middle look like the yellow blob upstairs, and so up to the factor of 1/2. So we get 1 over exponent minus 1. S plus 1 halves take away 1 is s minus 1 halves minus 1 over 2. And if I subtract 1 from the exponent, I just get s halves. Great. So this becomes 1 over s minus 1 minus 1 over s. And if I negate the first term upstairs and downstairs, then I make the whole thing look more symmetric. So this is what that middle integral in green, right, in the green thing that we had left over up at the top of the slide, right, that's for the real part bigger than 1, those exponents, s plus 1 over 2 and 1 plus s halves, have real part bigger than 1. So these calculations are completely legit. And once I've made them, well, fantastic. This expression now makes sense for all s. Okay? So meanwhile, the first integral up at the top of the slide, this part here makes sense already because the integral is only going down to 1. This integral, this is an entire function. This converges for all s. Right? It's an analytic function that already makes sense for every number s in the complex plane because of the decaying property of the theta function. And so that first integral makes sense everywhere. And now that green integral, we just calculated it. And that formula at the end also makes sense everywhere except for simple poles at 0 and 1. And so now we finally have our analytic continuation. So we're going to integrate down to 1. What was it? We had this theta minus 1 over 2 times u to the s over 2 plus u to the 1 minus s over 2, multiplicative integral du over u. And then we're going to subtract 1 over 1 minus s, subtract 1 over s. And so here are your polar terms. And this is already an entire function. And so that extends the completed zeta function to the whole complex plane. Except we have simple poles at 0 and 1. And if you look at those parts, s equals 0, you have your pole, you have your minus 1 over s. And minus 1 over s at s equals 0, it has a pole with residue minus 1. But the first term, you have 1 over 1 minus s. But of course, to write it as a pole, you really want to be thinking about 1 over s minus 1. This is the standard way you write things. S minus the number. So at s equals 1 minus 1 over 1 minus s, it is just 1 over s minus 1. Oh, okay, that has a simple pole, and the residue there, the numerator is just 1. And so we get simple pole with residue minus 1 at 0 and residue 1 at s equals 1. Okay. Are there any questions? That completes the analytic continuation up to one gap in the argument. why in the world is the theta function satisfying this property? Yeah, that was the one step that we didn't explain. Any questions? Anything here? Nope. All right. So we have 6 minutes, so we're certainly not going to be able to go through the whole thing here, but the idea is, so the theta function is a sum over all integers. This would generalize in higher dimensions to being a sum over a lattice. In any case, we have e to the minus pi n squared u, okay, for positive numbers, right? And so what is so special about this function that we can relate its value at u and 1 over u in this way? Do I have the dinos? Oh, the Domino's receipt. Was there enough? Was there enough pizza? Yes. Okay. All right. So the point is that, we're going to relate this to the Poisson summation formula. And what the Poisson summation formula says, it says that for nice functions, nice enough, roughly speaking, if it decays really quickly when the variable on the inside goes off to infinity, for nice functions, f of x, if you sum the function on all integers, the fact that that converges is already a serious thing, that this is equal to the sum over all integers of its Fourier transform, where the Fourier transform of a function is defined to be an integral of the function against a complex exponential. Whoops, sorry about that. All right, so let's try to parse what's happening here. So this is the Poisson summation formula here. And here's the definition. The Fourier transform, you start with the function f on the real line. The transform, the Fourier transform is an, oh my God, good grief, what a terrible mistake I've made. The only place where the original variable shows up, right? If we had, right, your new function f hat is a function of y, and y shows up only in one place, right up there in the exponent. Everything else is your integration variable x. This is a new function, and so the point is, if your function is e to the minus pi x squared, kind of miracle, its Fourier transform happens to be itself. And from this property, you can derive that if your function is e to the minus pi x squared t, let me just make sure I have this. I don't want to make another mistake here. Right, e to the minus pi x squared t, then its Fourier transform is 1 over root t times e to the minus pi y squared over t. And so when t is 1, you get back to the first statement, but you can, right, so when you know the function is its own Fourier transform, if you rescale it, as I did in this way, that the Fourier transform of this rescaled thing can be calculated out. And so then, what was that? Oh, okay, no problem. And so then you can apply the Poisson summation formula to e to the minus pi x squared t. And so on the left side of the Poisson summation formula, you're summing f of n, e to the minus pi n squared t. And on the right side, you're going to be summing the Fourier transform, which I gave you there. It's 1 over root t evaluated at y equals n on the integers again. And so this thing on the left is a theta function. And if you take out the 1 over root t, you're going to get 1 over root t times theta of 1 over t. Okay, so the key thing is that you happen to have this function e to the minus pi x squared that's equal to its own Fourier transform, and you do some manipulations from that, feed into Poisson summation, and the transformation formula for the theta function pops out. Okay, so when we want to apply this to quadratic forms, replacing n squared, a one-dimensional positive definite quadratic form, with a more general q of n or q of x, where x is an integral vector, we're going to want a higher dimensional Poisson summation running over z to the k, and using a theta function for a particular quadratic form, you'll have a similar kind of transformation formula. And with that, the method of extending the Riemann zeta function to its completed form will carry through in a very similar way. Okay, so we'll see that later. So that's all for today. Are there any questions? Let's stop before we get to questions.